Welcome to this explainer. Today we're diving into something that is absolutely mind-blowing. We are talking about an incredible feat of human engineering that also happens to be one of the most perilous construction activities on the planet, tunneling through complex geological formations. We aren't just talking about digging a simple hole in the dirt here. We're talking about massive infrastructure projects navigating through towering mountain ranges and deep subsurface environments where the sheer, overwhelming scale and danger of the Earth itself is just a constant factor. Because, when we build above ground, we can actually see the environment, right? But underground, the Earth is a totally unpredictable antagonist. Subsurface conditions are inherently complex, variable, and honestly, highly uncertain. You could be drilling through solid, perfectly stable rock one day, and then suddenly hit a massive pocket of groundwater, or wildly unstable soil, or even lethal gases the next. Without incredibly rigorous, standardized safety protocols, this underground construction can rapidly turn disastrous, as the ground literally shifts and fights back. So, the crucial point is that this unpredictability is definitely not just theoretical. It has very real, very high-stakes consequences. Recent incidents in India serve as some pretty stark reminders of this. Take the 2023 Silkyara-Barkot collapse, for example, where 41 workers were trapped for 17 agonizing days after a section of the tunnel caved in. High-profile, catastrophic events exactly like this, alongside the 2019 Mumbai metro collapse, became the vital catalyst for drafting India's comprehensive new national guidelines for tunnel safety, which is exactly what we're breaking down today. So here's our roadmap for the explainer today. First, we'll look at the high stakes of tunneling. Second, decoding geological hazards. Third, the risks of drill and blast. And finally, engineering safer ground. Okay, let's dive right into this. Section 1. The high stakes of tunneling. Before a single piece of rock is even moved, a staggering amount of rigorous planning has to happen to ensure a project doesn't end in disaster. Safe tunneling requires a massive, multi-phase lifecycle framework. We're talking non-negotiable steps across the pre-construction, construction, and operation phases. During pre-construction, engineers absolutely must produce geotechnical baseline reports and detailed hazard assessments. If the risk levels aren't acceptable, well, they have to develop a mitigation plan before regulatory approval is even considered. It's just a continuous, relentless cycle of monitoring and instrumentation all the way through to maintenance. Moving on to Section 2, decoding geological hazards. Let's look at the specific, invisible antagonists engineers have to bottle. Seriously, think about it for a second. What actually happens when the Earth fights back? We really have to stop thinking of a mountain as just a static pile of rocks. In tunneling, the mountain is an active, tremendously heavy force. It's under immense pressure, and it continually resists human excavation through dynamic movements, unpredictable water flows, and even toxic gas releases. The Indian guidelines break down these massive, chaotic primary hazards and contrast them with the precise human interventions needed to neutralize them. For rockfalls, the control is mechanically scaling the rock and securing it with bolts. For a massive face collapse, engineers rely on ground improvement techniques and meticulous tunnel boring machine selection. Water ingress, which, by the way, can flood a tunnel in minutes, requires pre-grouting ahead of the excavation face and installing robust drainage. And for hazardous gas emissions, the solution is continuous ventilation and automated gas detection systems with lockouts. It is literally a high-stakes game of geological chess. Now, one of the most fascinating and, frankly, terrifying hazards is something called squeezing ground. Imagine excavating a hole and the walls literally start creeping inward to crush you. That is squeezing ground. It involves weak, plastic rock or soil that undergoes time-dependent deformation. Because the ground around the excavation becomes overstressed, the earth plastically moves into the tunnel space. To survive this, engineers can't just build rigid walls. They actually have to install flexible supports, like compressible layers or sliding steel ribs, that absorb that deformation before the tunnel is completely crushed. But on the totally opposite end of the spectrum from that soft, creeping soil is the hazard of hard rock, the rock burst. A rock burst is the sudden, violent ejection of rock fragments from an apparently stable underground excavation. This happens in deep tunnels where the in-situ stress is just massive. When it fails, it can release explosive seismic energy comparable to a magnitude 4 earthquake, sending thousands of tons of rock flying. This is a terrifying reality, which is exactly why the guidelines mandate that engineers must use microseismic monitoring to detect warning signs and predict these violent explosions of stone before they ever happen. All right, bringing us to Section 3, risks of drill and blast. When dealing with hard rock, you often have to enter the combat zone of explosives. Now, what's really interesting about this is the massive contrast between intention and reality. On one side, we have the exact engineering goal, controlled fracture. This means systematic drilling of blast holes, loading them up and using controlled detonation to fracture the rock incredibly precisely. But on the other side, we have the highly volatile, lethal risks. Misfires, where explosives just don't detonate. Chimney formations, where the roof collapses upward. Excessive loosening of the surrounding rock. And the sudden release of toxic blast fumes like nitrogen oxides. So, to protect workers from these extreme hazards, the new guidelines lay out some absolutely non-negotiable safety protocols. Wet drilling is mandatory to suppress respirable crystalline silica dust, which is a major respiratory hazard. Only licensed and competent explosive handlers are allowed anywhere near the charges. If there's a misfire, strict clearance procedures by authorized personnel are enforced before anyone else can approach. And finally, mandatory ventilation of all toxic blast fumes has to be completed and the atmosphere fully inspected before the crew is allowed back in. So, how do engineers actually win this battle? Section 4, Engineering Safer Ground. When facing weak or soft ground, the whole strategy relies on a critical chronological sequence. Step 1, excavate rapidly but in small headings. Don't try to take out too much at once. Step 2, stabilize the newly exposed face immediately. Step 3, apply the primary lining within the ground's stand-up time. Stand-up time is basically this brief window, a ticking clock before the unsupported ground collapses under its own weight. In tunneling, this timing isn't just a schedule, it is the literal difference between success and a catastrophic cave-in. Engineers have to mathematically match highly specific support types to specific ground behaviors. If they're anticipating block falls, they deploy flexible support, like fiber-reinforced shotcrete and pre-tensioned bolts. If they're dealing with a rock burst scenario, they require full column-grouted ductile rock anchors immediately after excavation. Every single geological temperament has a designated, heavily engineered countermeasure. Now, when the ground is exceptionally weak, advanced ground improvement techniques become the ultimate line of defense. First up, forepoling. This involves inserting steel pipes ahead of the excavation phase to create a sort of protective umbrella over the workers. Then there's face grouting. This means literally injecting cementitious or chemical grout directly into the fractured tunnel face to glue the unstable rock together and stop water inflow. And finally, a temporary inverted arch. This involves shotcreting the floor of the tunnel immediately after excavation, closing the tunnel ring so that the immense, crushing pressures from the sides and top don't cause the floor to heave upward. Ultimately, tunneling is a profound battle of physics, geology, and human ingenuity. It requires anticipating every single possible way the Earth might react and having a proven, highly regulated system ready to counteract it. So, I'll leave you with this thought. The next time you travel effortlessly through a mountain tunnel, will you look out the window and consider the invisible, highly monitored, and fiercely regulated engineering that is holding millions of tons of earth back just to keep you safe? Thanks for joining us for this explainer, and keep questioning the world around you.